Okay. Because really we're here to learn from each other because a lot of this old equipment can be on the dangerous side. And as the title said, things that can kill you. And in fact, with all our solid state equipment, we forget what working with that old stuff used to be like. And I've gotten some nasty pokes, and you're going to hear a lot of woulda, coulda, shoulda. So, anyways, okay, things that can kill you. Your high-powered amplifiers, a little bit like that one back there, you probably have a couple thousand volts on that thing. And again, with a heavy-duty power supply, capacitors, and everything else, it could be nasty. It could be fatal. And even the old, like a 75-watt rig. I guess I'm thinking DX40 or something like that with the 6146. You got 750 volts there on the plate. And one of the worst pokes I ever got was, again, a pair of 6146s, had a relay that was chattering. And I said, well, gee, if I just press it in, maybe the relay will seat. Guess what? The relay was hot on top, and it hurt. Yeah, and if you look at receivers with transformers in them, typically they're 250 to 350 volts. And so again, that stuff can hurt. The other one here is your AC, DC radios. We forget that these radios back in those days did not have a polarized plug. And one side of the line was grounded to the chassis. And I've gotten nasty pokes on that where you think it's ground, and guess what? It's not ground. And then I see a couple of the old timers there laughing about it because they've done it, haven't you?
I'm glad I had wheels on my chair.
Yeah. And as you slide past, it's a little bit like the joke, gee, the radio fell in the bathtub with the kids. But don't worry, the radio's okay. So anyways, just some things to watch out for there, and as a little bit of an introduction. Okay, before powering up, like back there, that really looks quite clean. And essentially vacuum the thing out, really look for any kind of damage. Things like resistors in that typically will be relatively brown. They could be a little bit on the brittle side. They do change value in that as they age. But especially be careful of the variable capacitors. It's so easy to bend those plates and short them out. And also with the high-powered stuff, guess what? You got to be real careful of arcing there. Right, Craig? But look for leakage. Use a rag, wipe down the tubes and things like that. And especially look for frayed insulation. Power cords are just horrible for that kind of thing. And the cracks and everything else, and who knows if you're going to short them out or whatever. Yep. Absolutely. Oh, the bill here was saying a common upgrade is going from 2-wire plugs to 3-wire plugs. And of course, watch what you do with the neutral. The other thing is that you still may not be safe. You really ought to test the receptacle that you're plugged into. If someone wired the thing backwards, guess what? You're in as much trouble as before. And also you may have to disconnect the ground because again, that one leg is again shorted to ground. Seemed like there was something I wanted to mention. Absolutely, a hot chassis, and yep. And there are times that even an isolation transformer doesn't protect you because there's capacitance between the windings. I gave an electrician a reasonable poke on a 3 kW melter because, hey, no problem, you can touch it. Well, he wasn't real happy about it, and he reminds me a lot of times. Seemed like there. Oh yeah, yeah.
No way, too, if he's gonna fire that thing up, you're gonna have to, you gotta fire it up slow. You just can't put full power on it. What's the condition of that output tube, you know?
Absolutely. I think I went a little bit too far. Okay, you go to power something up like that. Yes.
Can you turn that up? Is that possible? Make it a little louder.
Okay, the audio.
Yeah.
Okay. I will speak closer. You know, if the thing is not very valuable, you can give it the old smoke test. You know, you're not going to fix the thing if it breaks. At that point, plug it in, turn it on, watch for smoke or whatever. You know, it's a quick and dirty test, and seems like half the time that's about what I do. Much better, of course, is reduced voltage here. And Craig, like with your amplifier there, I think that you had a sale that was going to happen, and then the guy reneged because he wasn't sure of the tubes and he wasn't sure of a lot of things. And so, how many years had it been since it had been used? Okay, I was wondering how many years it had been since the amplifier had been turned on. Okay. Okay, so 30 years, you know, what about the capacitors? What about a lot of things? And so, you know, using a variable transformer, the reduced voltage, at least it shouldn't smoke as bad if something is going wrong. The other thing is that things like tubes and that, the inrush is hard on them. You know, your light bulbs typically burn out when you flip them on. You know, essentially the current goes in there, the shock of the heating up, the expansion in that, and guess what? That's where it goes. So anyways, Craig, on your amplifier, what I did was it was set up for 240 volts. I put 110 on it. And I just let that thing sit and cook for probably a couple of hours. And at that point, I was looking for gassy tubes. I was looking for any kind of smoke. You know, basically check it over and let the thing cook for a while. There's a whole bunch of things on the internet that if you do have a bad tube, you can do. You know, it might be apply high voltage to the filament for a short bit, and you may have one chance of doing it. It may be high current for a bit to burn off crap that's on the plate or something like that. But again, you have one chance, and the best thing is not to push it too hard. Again, sitting there and cooking, what you'll find is that some of the gases and some of the crud on the elements and that will actually burn off, and they will actually go back into essentially the vacuum. A major thing, oh yes.
Electrolytic capacitors are famous for dying.
Absolutely. Electrolytic capacitors, and again with reduced voltage, what happens is the way an electrolytic works is you've got a plate and then you've got an electrolyte in there, and the voltage actually pulls some of the ions away from the plate, at which time then it forms the, essentially a microscopic insulating barrier between the two. And if those things dry out, guess what? Easily arc, easily, well, actually, most of the time, I was going to say most of the time the capacitance goes way down too. But again, reduced voltage, at least you don't shock the electrolytic. You can reestablish the ions in the solution. So, yeah. You know, I think that they've improved it a great deal because, I was wondering in terms of have they improved, have they improved the electrolytics? Back, I'd say pre-1970, they were horrible. They seem to be pretty good right now. In fact, Craig, I was really worried about your L4B. What would those capacitors do? And basically it was no problem. Again, reducing the voltage at least gives you a chance to save it. It at least gives you a chance of not having a catastrophic type of failure.
Yeah, the old ones with paper, they were really crappy.
Absolutely.
I have a Mallory 1000 microfarad capacitor, and it's sealed in plastic. It's like 40 years old, and I tested it. It's perfect.
Yeah. Some are good. Yes.
I was just going to say there was that window there where the Chinese sort of took over the capacitor or the electrolytic capacitor market. They didn't know how to manufacture them properly. They put Sprague and everybody out of business, and then all of a sudden there were all these power supply failures back in the 80s. So computers and stuff like that.
And actually, several years ago, I was in the process of restoring an old Hammerlin SP 600. And anyways, these capacitors here are known as black beauties of death. I'll pass that one around. But anyways, they're beautiful, nice, shiny black cases and so forth. And guess what? They're not any good. Yes.
So when you do that, you separate the high voltage and then power it separately or lower and keep the plate voltages so that they just on the standard transformer, or how do you do that?
Tim, George was asking what do I do with the power supply and that. Typically, I just leave everything there. Start out with low voltage and essentially see what's going to happen. A lot of times you don't have a variac here, but even a fixed transformer. Essentially, a 120/240 volt transformer. At that point, then you can hook the thing back up again and basically put half voltage on it. It's again, it's a good solution.
Use the 240 winding on 120 volts.
Yeah, and that's exactly what I did with the L4B.
Oh, you did?
Yes. Nope, I didn't use a variac. And again with the woulda, coulda, shoulda, maybe I should have used a variac and slowly varied the voltage, brought it up nice and slow. The other thing is if you can limit the current, you can limit the damage. And a good way to limit current is with a light bulb. Well, actually a fixed resistor is even better, but a light bulb is quick and dirty, and it really does a pretty good job. I've got a little setup that I have a 40-watt light bulb, and so maximum power I can put into something is about 20 watts. You match the power of the light bulb to the load, and so anyways, at that point at least you don't have huge amount of damage. One problem with the light bulb, though, is it starts out at close to zero resistance. And so you do end up with a quick surge there. And that's where a fixed resistor would be better. But again, if you look at a fixed resistor, you want to limit the current to 1 amp. That's 100, that's about 100 ohms. And if you had a short on the rig that you were testing, that would put 100 watts on the thing, which gets to be a little hard to find one. Even a 25 watt one, at least they'd give you a quick indication of what was there. So, anyways, smoke test, clean it out, bring it up slow, and watch what happens.
How did you determine those capacitors were bad?
Yeah. Ask how did I determine the capacitor was bad? I assumed they were bad. Yeah. And so it was time to replace them with a disc ceramic. And one of these days I need to finish the job and put the radio back together. Yes. Oh, yeah.
Electrolytics, you look at it, the end of it has a rubber end of the capacitor. One glance at those, you see a little bulb, a little blister of rubber. You know right then and there they're bad. Don't even put power to it.
Yep.
Take a pair of diagonal cutters and honk those off and replace them. It's a miracle.
Yep. Actually, to repeat the comment was, if you see any kind of bulge on a capacitor, it's bad. Get rid of it. Don't even power the thing up. And it's amazing what damage an exploding capacitor can do.
Where are your safety glasses?
Yeah. So, yes.
So what kind of capacitors are those? They look like 2-watt resistors or something.
Yeah.
Like that.
Actually, those capacitors that I passed around were 0.01s.
Those are 0.01.
0.01 capacitors. What's that? No. I don't know why they go bad, but anyways, it may have been some great idea.
Or ceramic or paper?
Yeah.
You think those are paper? That's the
Yeah.
reason why they look wound. Interesting. I've seen a lot of capacitors, and I've never seen a
Yep.
style like that.
Yep.
And that many too. What a
Oh yeah. It.
Paper dielectric, and that paper absorbs water from the air.
interesting.
They're all hygroscopic to some
And
degree.
that's probably bakelite or something that's around the outside.
Yep.
So it's
Cheap and dirty.
well, it's all they had back
Yep.
40, 50 years ago.
Yeah, exactly. And actually, that radio is out of the mid to early 50s.
What radio was that out of?
That's a Hammerlin SP 600.
You mentioned it. That's right.
Yeah. Okay. Oh yeah. Yeah. And if it doesn't glow, it means that you're not drawing much current. If it glows nice and bright, you probably have a problem, and like with the 40-watt bulb, that says probably you're drawing more than a half an amp. Now you put a 100-watt bulb in there, you're probably down to 1 amp. So, it's a good indication. If you're troubleshooting your car, you're blowing fuses, use a light bulb in place of the fuse. Essentially, that will protect everything, and when the light goes out, you found it. Yeah. Yes, right. There may be, the question was, you use a filament, and is there inductance there? The old dummy load back in the 50s and 60s was a 75-watt light bulb. And really, the SWR was not bad.
If you haven't used a light bulb as a dummy load, you
Yeah, yeah, it,
Kinda cool.
yeah, it works great.
When I was in high school, I had a CB radio, and that was roughly 5 watts.
Yeah.
Just a number 47 volt radio.
Right, exactly.
That's what Heathkit did with the tour and the sixer.
Yeah, and then essentially you tune for maximum brightness on the light bulb, and it works reasonably well. Okay, capacitors. They have a high failure rate, and they can explode. I've got a picture of one on an amplifier that I built that exploded and actually took out the second one. And I don't know if you've ever played with putting the voltage opposite on a. Okay. Yep. And guess what? You end up with paper and foil all over the place.
Things explode out the end, and they unfurl as a curlicue
Yep.
strip of foil, way long out in this.
And guess what? That shorts out everything else. Okay. Again, I mentioned a low voltage may help save a capacitor, but it may not. Okay, repairing an amplifier, that's where really this discussion came out, is that I basically checked out Craig's L4B, trying to bring a little extra value to it, and also not to screw anyone else that would buy it and end up with problems. Does it work? And so anyways, you asked me at that point then, well, gee, would I talk about how did I look at an amplifier? So anyways, that's where this discussion came from. And as you're working on, let's say, high-powered amplifiers, all the safety stuff that you do with it applies to the lower voltage, just that things are not going to happen maybe as fast or as bad, or it may not kill you, but it may really hurt. So anyways, that's just sort of an introduction to this. Bill, you may want to comment on this first comment here. More power, more problems. And you got a QRP rig and 5 watts, you got maybe 12 volts RMS going out to the antenna. You're not going to fry too much stuff like that. A 100-watt rig, you got 70 volts going out to the antenna. Probably not too much bad's going to happen then. But you get to 1500 watts, the legal limit, and guess what? You got 273 volts there, RMS, and your peak voltage is up there around 387. And RF loves to ionize things around it, jump out, and arc. And Bill, I know that you actually did a presentation once in terms of when you went to, I think, 1,000 watts, all the things that you found wrong. And I'm going to pass the mic over to Bill here and let him comment.
Let's see, how much time do I have? Yeah.
As much as you
Yeah, I have blown out traps and trap antennas that were listed at 2kW, and they just weren't. So I built my own, and various things fail, like the doorknob capacitors that are known to be pretty good at RF and high power. They aren't necessarily rated at high RF current, so if you've got enough current going through these things in your application, you'll just fry them. Also, on the peak power there versus peak voltage versus SWR, I've worked on 3, I think maybe 4 Ameritron high power amplifiers. Everything from the AL80 all the way up to the 1500. Every single one of them showed the antenna side loading capacitor on the Pinette had melted plates. melt. I mean, yeah, it start arcing, and frequently the operator doesn't know it because the amplifiers are pretty well shielded. They got blowers going. They don't hear it. They don't necessarily see it on the meter, but when they go through tuning these up, if they don't start at low power and work their way up slowly and get that plate or the tuning cap where it should be, you're going to start arcing. Once you start an arc, then the next time it's going to arc easier because you're starting to melt the plates and they start gravitating towards each other. And what was a 2,000 volt cap is now 1,000 volt or 500 volt. Eventually they start having troubles even with a good SWR. So very sensitive to that high SWR problem. And if you look at that capacitor, it looks like it's rated at 2,000 volts. So why they all have, it's a standard output design for all of the Ameritron amps. And like I said, I think I've seen it on all of every one I've worked on. In fact, Rob, you had me, where's Rob? Oh, you had me work on one for HRO once, same thing. The guy obviously didn't know what he was doing. He messed up the wiring on the AC transformer and all, but he got it going enough that he was able to burn the plates. So anyway, very good point there.
Yeah, it's one that the guy didn't tune it. He melted a hole through the tube. That's 72.
Okay, Rob, let me repeat that comment. He did not tune it and melted a hole in the tube. Yep. Yep. And again, more power, more problems. Watch out because it can get you. Okay, here's the L4B. Actually, woulda, coulda, shoulda. I did bring it up on low voltage. Everything looked good. And gee, I'm familiar with the L4B. I cranked the loading about where it should be. I hit it with 50 watts where it should be. And guess what? Had an arc on the capacitor. Yep, the plate capacitor. And actually you can, with let's say a small tool and die file, you can file that down, which is not too bad. If you need to, you can use an emery board, but be sure and catch all the metal filings underneath with a piece of paper. But anyways, with Craig's amplifier, I shoulda, coulda, woulda in that.
Was that a fly that was living in there that you tried?
I don't know. It could have been a piece of styrofoam packing material. Because you really had it packed well and it looks so clean. No need to vacuum this one out. It looks good. Let's do it. And guess what? Mistake.
Do you know what year that was built? Do you know what year your L4B was built? Like 1970 or?
It would have been, let me think back. It would have been about 1980, I think.
Okay. Yeah. Essentially, the L4B is a 1980. I think they came out with the R4C line mid 70s. And if you look at the dollars back then versus now, it would be basically a $5,000 amplifier. So, anyways, so that's one of the things that can happen. Yes.
Larry, what do you think about the practice of using contact cleaner, the spray type contact cleaner, to go through those capacitors?
Actually, contact cleaner is not a bad idea, especially if you let it fully dry. And occasionally in some of these spots here, that can get a little corroded or whatever, and essentially the capacitor gets a little on the flaky side. So it would help. And also the contact cleaner, as you spray it in there, might blow off all the dust and crap that might be there.
I think it's is it chlorophane? What's contact?
There are several versions of it.
Yeah,
Yeah.
exactly.
Yeah. Yes, yes, all the good stuff is now banned by the EPA.
Effective stuff,
Yeah.
not good stuff.
Okay, this is an amplifier I built. And anyways, notice the failure there of the electrolytics. Again, I think this one here was the first one to explode, which then took out the second one. So guess what? Be careful with them because they can do a lot of additional damage. The power supply that I was using was really quite stiff, 50 volts at 100 amps. So a 5 kW power supply, and the inrush could be quite high on those capacitors, which may have damaged them. Talking with W6, I was going to say, talking with W6PQL, it sounded like this may have been a fairly common failure mode. But anyways, you can see the damage that a bad capacitor will do. And here is a couple of the transformers, and notice the ferrite core, the burning it did there, and notice the burning it did on this side over here. The crap that is on the Teflon insulation of the coax in them. It gives you an idea of how much heat there is. And again, with high-powered amplifiers, when something goes bad, typically it's obvious.
Do you know what kind of insulation was on that wire?
Yeah. This is a Teflon insulation.
Teflon.
Yes. Yep. Absolutely. Okay. Here happens to be a bandpass filter. Notice the burnt capacitor over here. And actually, there should have been a second one here, which I think that failed, and it took off. It started to take off this one here. Notice the black carbon that's there. And again, notice the burning in that of the trace. So anyways, again, a lot of times if something goes bad, visibly you can see it. Actually I was using a couple of modules, and the two modules was really a poor idea with the balancing loads and everything else. And essentially a single module puts out 1200 watts, and because of the third harmonic coming back from the filters and that, with two modules you may get 1400 watts. So the difference of 200 watts is not worth it at that point. So again, I went back to a single module, and I had a spare. Some of the stuff is not quite so obvious. This is the final right here. Essentially, that is a 1200 watt transistor. And anyways, I had been running QSK full break-in for many, many years, and guess what? The vacuum relay failed, set up high voltage, and notice that literally burned through the drain tab. And so anyways, there's that gap right across here where the drain tab had gotten burned. And believe it or not, it still works. Yes, absolutely. It's a really tough transistor as long as you don't get too much feedback and you blow out the gate.
Yeah, I'll say that.
Actually, they're about $200, which is not too bad. It sure beats a 8877, which is I think about $1,500. And so I can afford to lose a few of those and still be okay. And Bill, you may want to comment on this one. Yeah, I don't know if you all remember Robert, but anyways, a interesting guy that was not afraid to experiment, and he was doing all sorts of crazy things. But anyways, when he got put into a home, when the Parkinson disease got bad enough, we had an estate sale. And so one of the goals was to get as much money for the estate as we could. And I had no idea what this amplifier was like, if it even worked or anything else. And Bill, I don't think you did either. Yeah. And so anyways, Bill gave it to me and says, okay, let's see what happens. So anyways, checked out the alpha. And anyways, when the high voltage was turned on, it would immediately blow a fuse. Yes. Yep. Yep. And as Bill mentioned, the original problem was a lightning strike. I didn't realize that I was blowing the fuse after the lightning strike. I would have looked at it differently. And so anyways, I really suspected bad capacitors. You know, again, with those kind of voltages and that, capacitors go bad. And I thought, well, maybe at full voltage, they were arcing over. But I saw no damage, I saw no bulging or anything like that, and I should have been suspicious then. So anyways, what I did was I disconnected the power supply from the load to isolate the problem. And I expected 10 volts on the voltage divider that feeds the meter that shows the plate voltage. That's when the excitement began. Okay, here's a diagram out of the manual. We got the power supply here. We've got the high voltage connection shorted to ground. And what I did was I disconnected the ground and I disconnected the high voltage. And I thought, well, gee, I can measure the resistance across R9 here, and it should be under 10 volts. Should be. Okay, what happened? Well, I tried to measure the voltage across that resistor, and with a freebie Harbor Freight VOM, and I drew a arc over 1 inch. And the meter still works. It's a little bit like the radio falling in the bathtub. It still works. But anyways, lifting the ground here, with the high voltage short to ground, there was a complex series of voltages. And essentially, we had the DC voltage, which was about 4 kW, 4 kV, plus on top of that was another 2800 volt AC with a peak voltage of about 4,000 volts too. So at that point, we had roughly 8,000 volts peak. Maybe go back to this other slide. Let's see, whoop. Okay. Essentially, we got this voltage. We're charging up the capacitor here to the 4 kV. And then at this point here, we have the 2800 volt AC to ground. Oops. Surprise. And again, woulda, coulda, shoulda. You know, I shouldn't have been so focused on the capacitors. I should have learned the history of the amplifier. Robert was in a home at the time. I should have talked to him. And when did the amplifier go bad? And knowing that it was hit by lightning, it might have changed how I looked at it. And I was too focused on the capacitors failing at high voltage. Yes?
How did you measure that super high voltage?
Actually, I did not measure the super high voltage because I drew that long arc and I said, not a good idea.
How did you know that's what it was supposed to be, or how did you know what the voltages were?
I keep hitting the wrong one here. Okay. Here's your voltage divider network here, and basically 5 1 mega ohm resistors. And here's a 12K resistor here, so voltage divider. If I probably got both probes on this resistor at the same time, it would have been okay. But then again, I would have had the 4,000 volts plus to ground anyways, which could have been disastrous. So anyways, George, that was how I hoped to measure the high voltage. Oh, actually, the other thing I could have done, which would have been a whole lot safer, and that is using a transformer. If I only applied 6 volts to the primary, that would have reduced the voltage by a factor of 40. So 100 volts rather than, the 4,000. I should have checked the capacitors for shorts because that whole board there was a separate board on top, and it would have been very easy with an ohm meter to check the voltage to ground. And the other thing, which I hadn't really thought about, but there was no bleeder resistor there, and so I could have killed the power, and I still could have had 4,000 volts there. Could have. Luckily, I didn't, and I guess the final I should have expected the unexpected. Yes?
Good example of that was a Harris transmitter
Mm-hmm.
in California, station KFS. The bleeder resistor had cracked.
Ah,
It was on an MF transmitter, almost 476 hertz. And when Carol, my friend who was working with me on that thing, reached inside, he did not get shocked, but the bleeder resistor partially came back together, and there was a huge kapow, lots of little pieces of ceramic flying in every direction.
yep,
And those Harris transmitters were famous for that.
yep,
Because the Harris transmitter, the experienced and skilled radio guys there would summarily change the bleeder resistor whether it looked bad or not.
yep. And if I can repeat your comment, Harris a transmitter, and I think you said 4,700 volts or something like that on the plate. A bleeder resistor went bad, and a friend almost got electrocuted with it, but it went back together again and blew pieces of ceramic out at him. And so
It was on MF. It was 476 hertz.
oh, okay,
That was their CW transmitter for the watch frequency.
okay.
And it had died some years before that. They patched it up, just kept it limping. Nobody ever bothered to check the meter, and it was just an accident waiting to happen.
Yep. And again, expect the unexpected. If possible, I like to take a screwdriver and short across the capacitors, and I've lost the tips of a few screwdrivers. Yes, Bill?
Following up on the expect the unexpected, when I was in high school, I built a 1 kW amp. Didn't have an Elmer, so I was on the steep part of the learning curve. I flipped the amp AC power switch off and proceeded to go in and check something with a screwdriver. The contacts on the AC relay froze. They melted. So I still had 4 kV on there when I went in and hit it. Fortunately, it was wintertime. It was in the garage. I had a jacket on, but it blew a 1/2-inch hole in my thumb and completely burned out a huge hole in the jacket. Fortunately, the path was just through my arm. But there again, you can't always assume those relays are going to open up too.
So do you have safety glasses on your list here somewhere?
No, I don't. And actually, there will be some more stuff later on in terms of safety tips, and I should have had safety glasses. Yes.
Since we're talking about what we did wrong, when I was again young and had
Here.
but worked on a high voltage supply.
Use the microphone. Use the microphone.
Okay, when I was young and building a high voltage power supply, I was testing with a meter and then I had it, but I'm going to show you what I did. I held the things up, but I left the leads, so I burned a hole in each one I had, and it blew me back on my ass. but luckily I was okay. But you got to be careful; those leads aren't insulated as much as the little ends of the probes.
So, anyways, are you anxious to work on amplifiers? Yeah. Yeah, essentially working on other equipment. It's not going to be as spectacular, as bad as, let's say, a high-powered amplifier, but the stuff can still kill you. While the voltages are lower, touching the wrong part can hurt. And a common mistake is reading the tube socket on the bottom side in the wrong direction. And what you think you're on the grid or the either that or the cathode, guess what? You're on the plate. So, anyways, just a heads up there. Okay, why so much damage? Well, again, when a capacitor explodes, it splatters crap all over the place. And short circuits can result in extremely high currents, which at times we don't realize. I'm going to have a couple of videos there of some shorts with 480 volts. But anyways, with those shorts, you say, well, gee, it's 480 volts. Well, guess what? The event takes milliseconds to happen, and the currents can be the same as what you got with the 480 volts. So, anyways, the insulation is burned, carbon is spewed all over the place. I'll pass this one here around, and this was the discharge of a capacitor on a plexiglass dish. And notice the molten copper that is actually plated out on the glass. And again, think of that in terms of going on the traces and everything else next to you. So anyways, if it works, I'm going to show you a video of a number 12 test lead across 480 volts. What's that? It probably would be 3-phase, but it was line to line, so essentially 480.
What's the highest voltage in your test? No, seriously, it's series parallel.
I think the engine runs up to 100
and we don't have any sound here, but anyways, they're reenacting an accident where the guy put a jumper lead across 480 and he got across the wrong terminals.
Use the mic.
Okay, right there.
Yeah.
Oh.
Yeah. And we'll do it again in slow motion.
Hey, Chad, kill the light switch right there.
You know, that's the kind of energy we're dealing with, especially if we have a real good power supply with a lot of capacitance.
So that was a reenactment?
Yes. And anyways, the guy was sent to the hospital and molten copper sprayed all over him, the safety glasses and him. Okay, here.
Larry, grab the microphone.
Yep. Okay. That is a meter that was improperly fused. And what happens, again, you vaporize the copper element, it plates out on the cold glass, and guess what? You got a short circuit. Let me kill this thing. Okay, I'm looking for the pause button here. Okay, I guess we got it. But anyways, I don't know how many of you basically have left the meter on amps, and guess what? You went back to measure voltage.
There's a reason why amps is on a separate jack.
Exactly. And basically thank God for the fuse in there. Otherwise you'd have something like that. Let's see, get back to a little bit of the stuff here.
Yeah, we mentioned the electrolyte and the capacitors. Usually it's potassium hydroxide.
Okay.
And that's not terribly poisonous, but it is caustic, about like lye.
So anyways, with the capacitor, you got a fairly alkali material there that can irritate you too. Okay, let's see.
You know the old CRT TVs? That was just a big, huge capacitor.
Oh, yeah.
Discharge, 27,000 volts on that CRT. And,
Yep.
That's all thing of the past now, but the old CRT, man, they were
Oh yeah.
very old.
Yeah, essentially with the CRTs, you had a flyback, a transformer. They would pulse the voltage real quick. You'd end up with a sharp spike, and you'd rectify the spike, which then stored in a capacitor. And that hurts too. I've done that one. In 65 years of ham radio, I probably have made all the mistakes possible, but I keep finding new ones. Okay. Well, anyways, it's very tempting to replace it with an oversized fuse. You know, you expect, hey, gee, if it's a short circuit, guess what? It's going to essentially blow anyways. It may not blow. And while we're talking about high voltage, be really careful with power lines. I have a friend, Ed, out in California, and he sheepishly admitted twice he's taken the neighborhood down with his 160 meter antenna. Yeah. And the other thing is, this is probably 10 or 15 years ago. I talked to a guy on 20 meters, and about a week later, I got his QSL card. And a couple days after that, I learned in the news that he and his son were putting up an antenna, got across the power line, and both were electrocuted. with his family watching. Yeah, be careful with that. And we had an engineer that got killed. A dump truck was dumping a load of glass cullet, and he hit the power line. Luckily, the driver stayed in the car, but it set the tires on fire, and this engineer went there with a fire extinguisher to put out the fire. And the field was so great, no one could even get close to him. So, anyways, be careful.
Robert, one other thing to point out with power lines is it'll draw an arc of 10 feet, so you don't even have to get.
Yep, it'll jump out and kill you. And I've got another video if I can find it real quick. But anyways, it's a 10 kV system, a ultra fine wire that doesn't even show up on the video, and they energize it. And really, the purpose of the video was to show what cotton does for a shirt versus your polyester. What the guy's going to do there is he's got a 10 kV system, a ultra fine wire, and that was real time. Now you're going to see it in slow motion. Yeah. And I think there's one more that is in extremely slow motion. But again, you don't want your family to see that kind of stuff happening. Okay. Notice the flames and the molten material that's flying out of there, the extreme heat that's flying out of there. And again with polyester, basically it can, I was going to say, at that point, it's basically a shrink wrap.
They used to say don't wear synthetic clothes on an airplane.
Yeah.
In case you got on fire.
Yeah, exactly. And I know for wildland firefighting, no polyester at all.
What's the source? What's the source of your video, Larry?
That is a safety video by Detroit Edison. And if anyone's interested, I can make a copy of it or whatever.
Is it on YouTube?
I don't think so. So, anyways,
For the recording, say again the source of your video.
okay. It's a safety video from Detroit Edison.
So how did you end up with it?
I did a lot of electrical safety stuff when I was working. And also I did some out at Suncor and that also. So anyways, it's amazing how much power there is in something like that. Okay, just about done here. Be safe. Learn from other people's mistakes. We make way too many ourselves. And so anyways, again, learn as much as you can from other people's mistakes. That's why I'm so open about the mistakes I made. And sort of a funny saying here, wisdom and knowledge are very different. Knowledge comes from learning. Wisdom comes from generally poor decisions. And I think I skipped a slide here. Yeah, some general safety tips here. Watch out. You're not focused on what you're doing, it's going to get you. If you're tired, it's going to get you. If you're frustrated, angry, in a hurry, it's going to get you. And be focused on what you're doing. Take a break and rethink the process. did a lot of real heavy duty installation, testing, evaluating, and at work. And essentially we would get the machine at like 6 in the morning. We would work 12 hours and give the machine back to production then about 6, and we were all tired. And what I would typically do with the crew is, let's go to the break room, let's sit down, let's relax, let's think about what we're doing, and before you reach or touch anything, think. Think about what it can do. Yes?
How many times did that save you?
You know, I'm not sure how many times that saved me, but it has kept me from doing some real stupid things, I think. You know, I tend not to count the number of times it saved me, but I do count the mistakes. and I do look back at the mistakes and try and learn from them. Okay, other comments? Yeah.
Like the plane accident that happened at
Larry,
public service line.
I don't think that this will reach.
We had an accident that occurred on one of our company's lines along the hogback. And they had one of these big semi trucks with the big dump feature on the trailer that came up like this, the whole trailer. And this relates to your tires on your car. People assume that those are insulating tires because they're made out of rubber, but they're not. They are actually semiconducting. Semiconducting merely means it doesn't conduct electricity as well as a solid conductor if you had solid copper tires, for instance, but it does conduct some energy. So anyway, this guy was backing up and he lifted his dump truck and went right into the line. Now, this is where the semiconducting comes from. If that would have been solid copper tires, then the current would have been so high it would have blown the fuse, because there was actually a fuse behind this. As I recall, it was only a 10 amp fuse, which is not very much of a fuse when you're talking on our on the public service system. So anyway, somebody started yelling at him that he was in the line. So he opened the door and jumped out of the truck and ran away and turned around to look. Well, all this time the current's going through the tires. And, you know, if it's only like an amp, but the voltage is 7,620, that's 7 kilowatts of energy being dissipated in the tire. So in short order, that's where you get the tires starting on fire. So the guy says, "My truck." So he ran back to the truck, but this time he didn't jump onto the truck. He reached up for it, and as soon as he grabbed the handle, the truck was at 7,600 volts. His feet were at 0 and electrocuted him. And realized this had a fuse behind it. Fuse didn't blow because until the flames and the tires started, and then finally the metal wheels hit the ground and enough current came and then it blew the fuse. Also, you were mentioning about things can be these automatic breakers. What happens is if you get a ground, like that little fine wire you're talking about, that's one of these little aluminum balloons, and it gets across the line, it'll short it to ground. Well, if it shorts it to ground and it draws enough current for a fuse, the fuse will blow and then the line's de-energized. But then behind that, as you keep going closer and closer to the substation, you have automatic reclosers. And what they do is that they see the current go, they open up, and then they close right back into the line. And the reason they do that, when they open up, the air deionizes, the arc stops. When they close it back in, you're back in service. But then some of them will do this 2 or 3 times. Depends on what all of the fuse coordination, because when you have these lines going out, you've got your fuses and your reclosers, sectionalizers, different piece of equipment going back, and they will close different times. So the sectionalizer will open up and do multiple times because it's watching for the recloser. If the recloser closes back in and it's still on, the fault's still there, it opens up and stays open. Well, now you've still got a huge amount of your system out, so the sectionalizer opens and closes the second time to see if the recloser's locked out. Well, if it's locked out, then it means at least you got several thousand customers back in and only a few hundred off. But you just need to be aware of that. And you may have seen this if you live anywhere near a substation. Your lights blink in the house. That's the recloser trying to re-energize that line.
And I think this is a key statement here. Just because you think it's dead, it may not be for long.
Right. And the other problem is these are protected by fuses. The lines, unless they're really close to substation, then they're even protected by things that would allow much more current to flow. If enough current doesn't flow when the line comes down, it won't blow the fuse or open up the sectionalizer. That's why when you see lines down, when you're in your car, they say stay away from those lines, because the lines may be down, but if there's not enough current, those lines can be energized. You go up to it, looks de-energized, you find out it isn't. This is especially a problem up in our mountains because the mountain grounding is horrible. You can have a live line fall right on the ground up there where it's really rocky, and there's not enough current to blow even a small fuse. So the thing's laying there, but it's still hot.
So anyways, yeah, be really careful around power lines. And I think I may have missed a slide, but think in terms of how important is it to your family that you get up this good antenna, that you work this rare one. They probably don't care. And it shouldn't be that big a deal to you that you risk your life. Yes.
Along with safety, we have to think about lightning too. In 1999, I was a contract scientist with NOAA in Boulder, and worked with atmospherics and whatnot with them, because I'm a planetary scientist.
Jim, you want to use the microphone?
Can't hear? Can you hear me? Yeah.
Oh, okay.
I think you hear me. Anyway, I had a situation in 1979, Memorial Weekend. I lived in eastern Arvada, right there near the border, right near Sheridan and 64th. Over Golden, a storm started brewing. Saw the storm. It was clear skies overhead in all of Arvada and Wheat Ridge and all this. And so I said, well, that storm's coming. I better disconnect my power cables, or my antenna cables. I was coiling up the antenna cable, and all of a sudden, one of my cables, I'm holding it, and it was like a Jacob's ladder, started arcing from the center pin to the shield, and and it hit me twice. And for 3 weeks, my boss at work at the university had to tell everybody, Jim is not on drugs and he is not drunk. It literally melted the bottom of my shoes. I had gum-soled shoes at that time, and it melted those. It melted my belt buckle into my stomach. And I actually talked and walked if I had like muscular dystrophy or something like this. I could not function for 3 weeks. I could not put two sentences together. And it hurt so bad when it did. It took all my muscles from my cranium to my feet, and it ripped them from a violent jerking. And it happened twice in a row. Bam, bam. And it was clear skies. It was beautiful. No clouds over Arvada. And so in 1999, when I was working at NOAA, I talked to my boss, Al Bedard, about that. And he says, oh, yeah. He said, lightning and static discharge can occur within 20 miles of the storm front. Yep.
Yep.
So we have to be careful about that.
Oh, yes.
I was working in Boulder Valley Farm area, so like 75th and Belmont. There was a storm brewing over Boulder proper in the city. And there was solar on this rooftop, it's a metal roof, and it's high on the peak. So it's getting kind of close. Maybe we should get down. But it was still real nice. As we're getting down, I'm hearing thunder. We're a few items very far away. There was one that literally came over us. Three different directions. I saw light flash. It was so quick. There were people on the ground that literally because it was so quick. Throwing tools, running around, not knowing what's going on. See, like, we were
Yep.
off to the guys coming.
What's that?
He has a comment.
Oh, yeah. Yeah. Mm-hmm.
Are you through with the presentation?
I was going to say, basically, I'm done here. The one other thing I forgot to mention here, be careful of metal jewelry. Yeah, exactly. And imagine having a necklace on and looking over a amplifier and touching the high voltage supply. Yep. And you notice I don't have any ring on either. So, okay.
Thank you.